The S-block elements occupy the first two groups of the periodic table and are divided into two important families. Group 1, known as the Alkali Metals, and Group 2, known as the Alkaline Earth Metals. Although both groups belong to the S-block and share many common characteristics, they also exhibit significant differences in their electronic configurations, physical properties, chemical properties, and reactivity. The infographic compares these two groups side by side, helping us understand how the number of valence electrons influences the behavior of each family. The most fundamental difference between Group 1 and Group 2 elements is the number of valence electrons. Group 1 elements have only one electron in their outermost shell, giving them the electronic configuration ends. Examples include lithium, sodium, potassium, rubidium, and cesium. In contrast, Group 2 elements possess two valence electrons with the electronic configuration ends. This group includes beryllium, magnesium, calcium, strontium, and barium. Since chemical properties are primarily determined by valence electrons, this difference is responsible for most of the variations observed between the two groups. Because Group 1 elements have only one valence electron, they can easily lose that single electron to achieve the stable electronic configuration of the nearest noble gas. As a result, they always form positive ions with a charge of +1. For example, sodium loses one electron to form Na, while potassium forms K. Group 2 elements, on the other hand, contain two valence electrons. They lose both electrons during chemical reactions to attain a stable noble gas configuration and therefore always form ions carrying a +2 charge. For example, magnesium forms Mg and calcium forms K. This difference in electron loss also explains the difference in oxidation states. Group 1 elements exhibit a fixed oxidation state of +1, whereas Group 2 elements always exhibit an oxidation state of +2. These oxidation states remain constant in almost all of their compounds because both groups lose all of their valence electrons to achieve stability. One of the most noticeable differences between the two groups is their chemical reactivity. Group 1 elements are among the most reactive metals in the periodic table because they need to lose only one electron. Since removing a single electron requires relatively little energy, alkali metals react extremely rapidly with water, oxygen, halogens, and acids. As we move down the group from lithium to cesium, reactivity increases even further because atomic size increases and ionization energy decreases. Cesium is therefore one of the most reactive naturally occurring metals. Group 2 elements are also highly reactive, but they are generally less reactive than Group 1 metals. This is because they must lose two electrons instead of one. Removing the second electron requires additional energy, making the overall process slightly more difficult. Consequently, Group 2 metals react more slowly with water and oxygen compared to Group 1 metals. For example, sodium reacts violently with cold water, producing vigorous bubbling and sometimes flames, whereas magnesium reacts only very slowly with cold water and reacts much more readily with steam. Another important difference lies in hardness. Group 1 metals are very soft because they possess weak metallic bonding. Each atom contributes only one valence electron to the metallic bond, resulting in weaker attraction between the positively charged metal ions and the sea of delocalized electrons. As a result, alkali metals are soft enough to be cut easily with an ordinary knife. Sodium and potassium are classic examples of this softness. Group 2 metals are considerably harder because each atom contributes two valence electrons to metallic bonding. The greater number of delocalized electrons strengthens the attraction between metal ions and the electron sea, producing stronger metallic bonds. Consequently, alkaline earth metals are harder, stronger, and more resistant to cutting than alkali metals. Density also differs between the two groups. Group 1 metals generally have lower densities and include some of the lightest metals known. In fact, Lithium, sodium, and potassium are less dense than water and can float on its surface. Group 2 metals, however, are denser because their atoms are packed more closely and possess greater atomic masses. Therefore, alkaline earth metals usually have higher densities than the corresponding alkali metals. The difference in metallic bonding also affects melting points. Since metallic bonds are relatively weak in Group 1 elements, they require less heat energy to break, resulting in lower melting points. Group 2 elements have stronger metallic bonds because of their 2 valence electrons, so considerably more energy is required to separate their atoms. As a result, alkaline earth metals generally possess much higher melting points than alkali metals. Although both groups belong to the S block, they show different behavior when reacting with water. Group 1 metals react vigorously even with cold water, producing metal hydroxides and hydrogen gas. The reaction is highly exothermic, and the released hydrogen may ignite, producing flames or even explosions with heavier alkali metals. In contrast, Group 2 metals react less vigorously. Beryllium does not react with water under normal conditions. Magnesium reacts very slowly with cold water but readily with steam. Calcium reacts moderately with cold water, while strontium and barium react increasingly vigorously as we move down the group. Despite these differences, both groups share several important similarities. They are all metals with shiny silvery surfaces when freshly cut. They are good conductors of heat and electricity because they contain free-moving delocalized electrons. Both groups have relatively low ionization energies and low electronegativities, allowing them to lose electrons easily and form positive ions. Both exhibit strong metallic character and act as reducing agents by donating electrons during chemical reactions. Furthermore, the reactivity of both groups increases down the group as atomic size increases and ionization energy decreases. The infographic also illustrates the underlying reason for these trends. In Group 1, the presence of only one valence electron means that losing this electron immediately produces a stable noble gas configuration, making these elements extremely reactive. In Group 2, 2 valence electrons must be removed before achieving stability. Although this requires more energy than losing a single electron, the process still occurs readily because S-block elements possess relatively low ionization energies. The comparison between Group 1 and Group 2 highlights how a single difference in electronic configuration produces major differences in chemical behavior. Group 1 elements have one valence electron, form +1 ions, are softer, less dense, have lower melting points, and are extremely reactive because they lose only one electron. Group 2 elements have 2 valence electrons, form +2 ions, are harder, denser, possess higher melting points, and are less reactive than Group 1 because they must lose 2 electrons. Nevertheless, both groups display the characteristic metallic properties of the S block, including low ionization energy, low electronegativity, strong metallic character, excellent conductivity, and increasing reactivity down the group. Together, these similarities and differences provide a complete understanding of the behavior of the S block elements and their position in the periodic table. Sodium is one of the most important S-block elements because it is essential for the normal functioning of the human body. Although elemental sodium is highly reactive and never exists freely inside living organisms, it is present in the body as the positively charged sodium ion, Na. Sodium is classified as an electrolyte because it carries an electric charge when dissolved in body fluids. It is the major positively charged ion found in the extracellular fluid, which is the fluid surrounding the body's cells. The infographic illustrates how sodium plays a vital role in maintaining fluid balance, transmitting nerve impulses, enabling muscle contraction, regulating osmotic pressure, and supporting many essential physiological processes required for life. One of the primary functions of sodium is maintaining the body's fluid balance. Water constantly moves between cells and the surrounding extracellular fluid through the process of osmosis. Sodium is the principal ion responsible for controlling this movement of water. By regulating the concentration of dissolved particles in the extracellular fluid, sodium helps maintain the correct balance of water inside and outside the cells. This ensures that cells neither shrink due to excessive water loss nor swell because of excessive water gain. Maintaining this balance is essential for the proper functioning of every tissue and organ in the body. Sodium also plays a critical role in regulating osmotic pressure. Osmotic pressure is the force that controls the movement of water across cell membranes. Since sodium is the most abundant positively charged ion in the extracellular fluid, it largely determines the osmotic pressure of blood plasma and tissue fluids. Proper sodium concentration helps maintain normal blood volume, supports healthy circulation, and ensures that nutrients and oxygen are transported efficiently throughout the body. If sodium levels become too low or too high, fluid balance is disturbed, leading to dehydration, swelling, or serious electrolyte disorders. Another essential function of sodium is the transmission of nerve impulses. The human nervous system depends on the movement of sodium ions across nerve cell membranes to generate and transmit electrical signals called action potentials. At rest, sodium concentration is much higher outside the nerve cell than inside it. When a nerve is stimulated, special sodium channels in the cell membrane open, allowing sodium ions to rapidly enter the cell. This sudden influx of positive ions changes the electrical charge across the membrane, producing an action potential. The electrical impulse then travels along the nerve fiber, allowing signals to move quickly between the brain, spinal cord, muscles, and other parts of the body. Without sodium ions, nerve cells would be unable to transmit information, making communication within the nervous system impossible. The infographic also highlights sodium's vital role in muscle contraction. Every muscle movement, from blinking the eyes to running, lifting objects, or even breathing, depends on sodium ions. When a nerve impulse reaches a muscle cell, sodium ions help initiate the electrical changes that trigger muscle contraction. This electrical signal eventually leads to the interaction of the contractile proteins actin and myosin, causing the muscle fibers to shorten and produce movement. Sodium works together with potassium and calcium ions during this process, ensuring that muscles contract and relax in a coordinated manner. Without adequate sodium, muscles may become weak, develop painful cramps, or lose their ability to contract normally. Sodium also contributes to maintaining normal blood pressure. Because sodium regulates the amount of water present in the bloodstream, it directly influences blood volume. An appropriate sodium concentration helps maintain normal blood pressure and adequate circulation. However, excessive sodium intake over long periods can increase water retention, raise blood volume, and contribute to high blood pressure in susceptible individuals. Therefore, maintaining a proper balance of sodium intake is important for cardiovascular health. The infographic shows that sodium is widely available in many common foods. The most familiar source is table salt, or sodium chloride, which is used in everyday cooking and food preservation. Sodium is also naturally present in milk, eggs, meat, fish, cheese, bread, and many vegetables. In addition, processed and packaged foods often contain significant amounts of sodium because it enhances flavor and extends shelf life. After being consumed, sodium is absorbed into the bloodstream and distributed throughout the extracellular fluid, where it performs its numerous physiological functions. Inside the human body, sodium is found mainly in the extracellular fluid, including blood plasma and the fluid surrounding body cells. In contrast, potassium is the major positively charged ion inside cells. This difference in sodium and potassium concentrations on either side of the cell membrane is maintained by the sodium-potassium pump, a specialized protein that continuously transports sodium ions out of cells and potassium ions into cells. This active transport mechanism is essential for maintaining resting membrane potential, nerve impulse transmission, muscle contraction, and many other cellular processes. Although sodium is essential for health, both deficiency and excess can cause serious problems. A deficiency of sodium, known as hyponatremia, may occur because of excessive sweating, prolonged vomiting, severe diarrhea, kidney disorders, or excessive water intake. Symptoms include weakness, fatigue, muscle cramps, headache, confusion, nausea, and in severe cases seizures or coma. On the other hand, excessive sodium intake, known as hypernatremia or chronic high sodium consumption, may lead to dehydration, increased blood pressure, cardiovascular disease, and kidney problems. Therefore, maintaining a balanced sodium intake is essential for normal body function. The infographic summarizes sodium's major biological functions very clearly. Sodium maintains extracellular fluid balance, regulates osmotic pressure, enables rapid nerve impulse transmission, initiates muscle contraction, and helps maintain normal blood pressure. Together, these functions ensure the proper operation of the nervous system, muscular system, circulatory system, and overall body physiology. Sodium is an indispensable electrolyte that exists in the body as the sodium ion, Na. It is the major positive ion of the extracellular fluid and plays a central role in maintaining fluid balance, regulating osmotic pressure, transmitting nerve impulses, initiating muscle contraction, and supporting normal blood pressure and circulation. Through the coordinated movement of sodium ions across cell membranes, the body is able to generate electrical signals, control muscle movements, maintain water balance, and sustain countless biochemical processes necessary for life. Without sodium, the nervous system, muscular system, and many other vital organs would be unable to function properly, making sodium one of the most biologically important S-block elements. Potassium is one of the most important S-block elements because it is essential for the proper functioning of nearly every cell in the human body. Like sodium, elemental potassium is highly reactive and is never found in its free metallic form inside living organisms. Instead, it exists as the positively charged potassium ion, K, which serves as a vital electrolyte. Potassium is the major positively charged ion inside body cells, known as the intracellular cation. This unique distribution allows potassium to play crucial roles in maintaining electrical activity, supporting normal heart function, transmitting nerve signals, regulating muscle contraction, balancing body electrolytes, and helping maintain healthy blood pressure. The infographic illustrates how potassium performs these essential functions and why it is indispensable for human life. One of the most important functions of potassium is maintaining normal heart function. The heart is a muscular organ that contracts rhythmically throughout life, and every heartbeat depends on precisely controlled electrical signals. Potassium ions help generate and restore the electrical impulses that regulate the heartbeat. During each heartbeat, potassium moves across the membranes of heart muscle cells, helping restore the resting electrical state after each contraction. This process allows the heart to beat in a regular and coordinated rhythm. If potassium levels become too low or too high, the heart's electrical activity may become abnormal, leading to irregular heartbeats known as arrhythmias, which can become life-threatening if left untreated. Potassium is also essential for nerve signal transmission. The nervous system communicates through electrical impulses called action potentials, which travel rapidly along nerve cells. Potassium works together with sodium during this process. When a nerve cell is stimulated, sodium ions enter the cell and initiate the electrical signal. Immediately afterward, potassium ions move out of the cell, restoring the original electrical balance in a process known as repolarization. This allows nerve cells to prepare for the next signal. Without potassium, nerve impulses could not be transmitted efficiently, affecting communication between the brain, spinal cord, muscles, and internal organs. Another major function of potassium is supporting normal muscle function. Every voluntary movement, such as walking, running, lifting objects, or writing, as well as involuntary movements like breathing and digestion, depends on properly functioning muscles. Potassium helps regulate the electrical activity of muscle cells and works closely with sodium and calcium to initiate muscle contraction and relaxation. Adequate potassium levels ensure that muscles contract smoothly and efficiently. A deficiency of potassium may cause muscle weakness, fatigue, painful cramps, twitching, or even temporary paralysis in severe cases. The infographic also highlights potassium's important role in maintaining electrolyte balance. Electrolytes are minerals that carry electric charges and help regulate numerous physiological processes. Potassium is the primary intracellular electrolyte, while sodium is the major extracellular electrolyte. Together, these two ions maintain the body's fluid balance, electrical neutrality, and normal cellular function. Their concentrations are continuously regulated by the sodium-potassium pump, a specialized membrane protein that actively transports sodium ions out of cells while moving potassium ions into cells. This active transport mechanism maintains the resting membrane potential required for nerve conduction, muscle contraction, and many metabolic processes. Potassium also plays a significant role in regulating blood pressure. A healthy balance between potassium and sodium is essential for maintaining normal blood pressure. Potassium helps relax the walls of blood vessels, allowing blood to flow more easily. It also promotes the excretion of excess sodium through the kidneys, reducing water retention and helping lower blood pressure. For this reason, diets rich in potassium are associated with a reduced risk of hypertension, stroke, and cardiovascular disease. Maintaining adequate potassium intake is therefore considered an important component of heart health. The infographic illustrates the pathway of potassium inside the body. After consuming potassium-rich foods, potassium is absorbed through the digestive system into the bloodstream and transported to various tissues. Most potassium enters body cells, particularly muscle cells, nerve cells, and heart cells, where it performs its essential physiological functions. Through its involvement in electrical signaling and cellular metabolism, potassium contributes to the normal functioning of virtually every organ system. Potassium is widely available in many natural foods. The infographic highlights several rich dietary sources, including bananas, potatoes, spinach, avocados, oranges, tomatoes, beans, yogurt, and green vegetables. Other excellent sources include sweet potatoes, lentils, peas, coconut water, dried fruits, fish, and milk. A balanced diet containing fruits, vegetables, legumes, and dairy products usually provides sufficient potassium for healthy individuals. Although potassium is essential for life, both deficiency and excess can cause serious health problems. Potassium deficiency, known as hypokalemia, may result from prolonged vomiting, diarrhea, excessive sweating, certain medications such as diuretics, or inadequate dietary intake. Symptoms include muscle weakness, fatigue, constipation, muscle cramps, irregular heartbeat, and impaired nerve function. In severe cases, hypokalemia can cause dangerous cardiac arrhythmias. Conversely, excessive potassium levels, known as hyperkalemia, may occur due to kidney disease, certain medications, or excessive potassium supplementation. Hyperkalemia can interfere with the heart's electrical activity and may also cause life-threatening arrhythmias. Therefore, maintaining normal potassium levels is essential for overall health. The biological importance of potassium becomes even clearer when compared with sodium. While sodium is the primary positive ion outside body cells, potassium is the primary positive ion inside body cells. Together, they establish the electrochemical gradients required for nerve impulse transmission, muscle contraction, heart rhythm, and countless cellular activities. The continuous movement of sodium and potassium across cell membranes, powered by the sodium-potassium pump, is one of the most important physiological processes in the human body. Potassium exists in the body as the potassium ion, K, and functions as the principal intracellular electrolyte. It is indispensable for maintaining normal heart rhythm, transmitting nerve impulses, supporting muscle contraction, balancing body electrolytes, regulating blood pressure, and ensuring proper cellular function. By working together with sodium through the sodium-potassium pump, potassium helps generate electrical signals, maintain fluid balance, and support the coordinated functioning of the nervous, muscular, and cardiovascular systems. Without adequate potassium, the heart, muscles, nerves, and many other vital organs would be unable to function normally, making potassium one of the most biologically important S-block elements essential for human life.